Let's go over the final example here, and that will be a combination of series and parallel connection. So here's a circuit. We've got, in this case, I've used a schematic representation of the resistor. So we have a 20 ohm resistor hooked up to a 5 ohm resistor, and these two together are combined with a third one, which is a 60 ohm resistor. And so we have a series of questions to try to answer on this particular circuit. So we would like to know what is the total resistance of the circuit, what is the total current, what are the current and voltage for each of the resistors, and also how much power is delivered by the battery and how much power is dissipated by each of the resistors. So to find the total current, we would need to know something about the total resistance. To combine the resistances, so we first notice that resistor 1 and 2 are connected in parallel, so we use the rule for parallel connection. So 1 over 20 plus 1 over 5 gives us a total of 5 over 20. When we flip that upside down, we get 20 over 5, which is 4 ohms, so that's the combined resistance of R1, 2. But then that is connected in series with R3, so when we use the series technique for that, that is the rule for adding resistors in series, we add together the resistance of 1 and 2 to the resistance of R3, so we get 4 plus 60. That gives us a total of 60 ohm for the overall resistance of the circuit. Now if we want to get the total current out of this, well, we take the voltage of the battery, 16 volts, and we divide this by the total resistance, and that would be 64 ohms now. So 16 over 64 gives us 0.25 amps. Now we need to find the current and voltage for each of the resistors in the circuit. So here it might be helpful to take a quick look again at this circuit. So 1 and 2 are connected in parallel, the 20 and the 5 here, and then the 60 is connected in series with these two. So if you take a look at the current in the circuit, you'll see that in this branch, from the battery, from the positive end of the battery, all the way until this point, we would be dealing with the total current. When we get to this connection point here, some of the current will go up through the 20 ohm resistor, some of the current will go through the 5 ohm resistor. The proportion will not be the same. There's more resistance up here, less resistance here. So choosing the path of least resistance, as we talked about in class, means that more current will go through this resistor than through that one. We can actually even predict that there will be 4 times more current through the bottom branch here than there is up here. The 4 is simply because 20 is 4 times bigger than 5, and so the current here will be 4 times bigger than what it is in branch number 1. But no matter what the numbers are, combined together, this will come back to the total current, because these two currents will recombine here and go on through R3. So R3 gets the total current, which then recombines here and continues on here, and you have a closed loop, so you'll get a total current of 0.25 amps as computed before. So what that helps with is the fact that we now know that the total current is also the current through I3, so we have the answer to that question. It will be 0.25 amps for the 60 ohm resistor right here, which also allows us to say that the voltage across that resistor is going to be 60 ohms multiplied by 0.25 amps, which gives us 15 volts. And then we use a rule that we talked about earlier for the series connection. Basically R12 and R3 are connected in series, which means that they have the same current, and so the 0.25 amps is going to go through both. But also they have the voltages add up to the 16 volts of the battery. So we just figured out the voltage across number 3, which was 15 volts. We know that that plus whatever the voltage of 1 and 2 has to be equal to 16. So that tells us that V1, the voltage across R1 and R2 here, is equal to 1 volt. It's also the voltage across R2 because they're connected in parallel. Remember that resistors that are connected in parallel have the same voltage. In this case it would be 1 volt. So once we know this, then we can figure out the current through resistor 1, we know its voltage, we know its resistance, so 1 over 20 works out to be 0.05 amps. And then for number 2, 1 over 5 works out to be 0.2. And so you can check that the current going through the bottom one, 0.2, is 4 times the current going through the top one, because here there's 5 times less resistance than up here. So everything checks out. And then the last point is to figure out the power. So here I've recreated a table like the ones we use in class. So we've got resistors 1, 2, and 3 listed here. Their resistances are 25 and 60 ohms. Combined resistance is 64. Again, it's not a straightforward addition because of the way these things are connected. We worked out the current through each resistor, 0.05 amps, 0.2 amps, 0.25 amps, which gives us a total of 0.25 amps. The current through R3 was already understood to be the total current. We've also worked out the voltages through R1 and R2. The voltage will be 1 volt. It's the same because they're in parallel. And then for R3 we had found 15 volts, and so those combined give us 16 volts here. And then to get the power, so in this case we get the power dissipated by the 2 resistors, we would multiply 0.05 by 1, and that gives us 0.05 watts. Here we'd get 0.2 times 1, which gives us 0.2 watts. And for R3 you get 0.25 times 15, which works out to be 3.75 watts. And then for the total power dissipation, or that would also be the power delivered by the battery, we get 0.25 amps for the current times 16 volts. That's a total of 4 watts. And we can check that the 4 watts provided by the battery have been used by the 3 resistors. 0.05 plus 0.2 plus 3.75 adds up to 4 watts. So these are the examples for this particular calculation and for the discussion of series and parallel connections in conjunction with Ohm's law for this particular section of the course.